Today I am going to discuss your next assignment, right? What are the tasks which you have to do, and then we will proceed on texture mapping, which we mentioned last time, right? So this assignment is basically going to be on ray tracing, right? So what you have to do is write a program for recursive ray tracing. So it's not just the basic ray tracing of level 1, it's recursive, which would include shadows, reflection and refraction. Okay. As far as the type of objects are concerned, just consider very simple primitives like spheres and planes. Okay. And one of the important component of this whole assignment is that you will have to simulate the process. So I will explain it more in details. In fact, it's something very similar to what you did in first assignment of implementing the viewing pipeline. Right. So there you simulated the process of viewing pipeline. Right. What are the various stages of viewing pipeline? So similarly, here you will simulate the process of ray tracing. Okay. So what let's look task by task. So first thing what we are saying is you need to implement the recursive ray tracing, so which we have seen, where the idea is that you have a specification of the eye, the specification of the viewing plane or the image plane, and then there is entire scene, right? And this scene, as I mentioned, would comprise simple objects with spheres and planes. Okay. So the idea would be that you will implement how to get the reflective ray, how to get the transmitted ray or the refracted ray, right, and do this tracing till a specified depth of your recursion, right, or when the ray escapes the scene. That means it does not intersect with any other object, right. So either of the two conditions. Okay. So this whole thing has to be implemented. So the data structure you would employ would facilitate you to form this tree structure of ray tracing. Fine. So then when I said that you need to have shadows, you need to have reflection and you need to have refraction, right. So what we are looking at is that given a primary ray through a pixel xy from I, what are the various other rays which may be emanated by the hit point, right. So they may be a transmitted ray, they may be a reflected ray, or they may be a shadow ray. So all these rays need to be computed. And then as far as the global illumination or the illumination at this point is concerned, you would use this global illumination, which would account for the local illumination computed at this point through the various light sources which are there, and also account for the subsequent reflective and transmitted rays, whatever illumination you obtain as a consequence of recursion, right. So you will have to do a global illumination computation to get the intensity or the color at this point, right. So, this is what we have already seen. Now, as far as the objects are concerned, I mentioned that you consider basically spheres and planes, right. So, you need to write the intersection routine for sphere and plane, right. With plane, I mean it is a finite plane. There are extents of the plane. Okay, so, it would also require you to do a containment test. First, you will do a test for the point on the plane and then figure out whether that point is contained within the extents of the plane or not. Fine. So, as far as the object ray intersection is concerned, you are basically asked to have the objects with sphere and plane. Okay. Now, so we have seen illumination, we have seen intersection. Now, what do I mean by doing this process simulation? Right. So, if you look at the way the viewing frustum gets formed, is basically with respect to the eye or the center of projection of the camera which you place, and there you have this image or the viewing plane, right. So, rays are started from here and they go through each pixel you define, and then the intersection is performed in this scene, right. So, basically a viewing frustum gets formed with the window you specify and the eye you specify, right. So, what we are trying to look at as a process of simulation is that such a viewing frustum now in the word coordinate system, because you are going to perform the intersection in word coordinate system. So, that is where it is going to be slightly different from what you did for viewing pipeline, right. So, you would show this kind of a frustum with this viewing plane, or which tells you that how many pixels you have considered for the window, right, the location of the eye, and then the idea is that some sort of a probing will be done with respect to a pixel or a point on this image plane, and you have to give the visual display of the trace of all the rays from that pixel. Okay, that is what I mean by this process simulation. So, let me elaborate on it. So, what do I mean here is that you have this eye, right. You have specified the window also, the extent of the window, which basically is in terms of how many pixels you have horizontally or how many pixels you have vertically, right. And with respect to each of these pixels, you figure out the appropriate coordinates u I v j, take them into the word, because that is where you are going to have a display. I is also in the word, right. And then you show this primary ray which is going from I to that pixel to the scene, right. And then figure out from the point of intersection the closest point of intersection, right. That is what you display there. Fine. So, these are some other objects may be there in the scene, there might be some light source. So, light source, for instance, you can show it with some yellow sphere or something like that. Okay. So, what are we trying to do? We are basically trying to see what happens to the ray which goes from this pixel as a visual demonstration. Okay. From an outsider viewer, I will see that yes, there is a ray starts from I, goes through that pixel, and this is the point of intersection I obtain, right. and then further there may be ray which is a reflected ray which goes and hits this object, right, another reflected ray which goes from here, and so on. So, all this rays which you obtain, you have to show in the process. Okay, this is what I mean by simulating the process. Okay, so it's in some sense a visual debugging. Right, you will see exactly what is happening to your scene. Fine. So, you have to specify, of course, the material properties and the color attributes for each of the objects you define, right. So, in addition to the geometric specification of the objects, you also need to specify the material properties of the objects, which includes the specification of your diffuse coefficient, specular coefficient, and so on, refractive index, right. So, these material properties also need to be defined. Okay. So, the idea would be that basically some probing is done. So, let us say I type in that, tell me what happens to the ray with respect to the pixel at location so and so, x and y, right. So, you will show the entire process to the ray in 3D, right, again using OpenGL, just the way you did it in your first assignment. That is fine. See, if
will it contribute to luminosity at that point?
yeah, see, what are we doing? We basically doing that. This is the point hit which we obtain.
Yes.
So, here we compute the illumination with respect to the light sources we define. That is the local illumination component. Same thing happens here. Same thing happens here. So, whatever are the hit points with respect to the secondary rays, we compute the illumination, right, and do the attenuation using the reflective coefficient and the transmitted coefficient, right. So, what I am referring to is this basically, right. So, there is a local illumination computation which is directly from the light sources you have, and plus these are the accumulated terms with respect to the secondary rays, the reflected ray and the transmitted ray.
So, for the computation of these secondary rays, I mean these are like what have been reflected from other objects.
Exactly.
So, sir, like we follow a certain order of taking up these objects and finding out the rays. Won't the order determine these components?
No, see, yes, there is an order in terms of how. Let me go back again. Maybe I have to go back to this. So, this is the primary ray you have, right. This is the first reflected ray. This is the second reflected ray, and so on. So, this is the order you have. And when you form the tree, right. So, this is the root node which corresponds to the I ray, hits this object C, right, and then there is this reflected ray and there is this transmitted ray. So, this is the next level of recursion, and then I go to the further level down, right, and then I accumulate the intensities. Is it clear or not? And every time when I come from here to here, right, the intensity which was aggregated will be attenuated by the reflective coefficient. right, gets multiplied by KRG, right. So now again going back to this process of simulating. So what I was saying is that when you probe for any pixel, one should be able to see the process of tracing the rays, including the secondary rays, what is happening, right, in 3D environment.
So now at that point on the sphere on which the reflected ray from the plane comes,
Right.
there might be a direct ray from the eye onto that point via some other pixel.
That's correct.
Which
So
will
that will be the primary ray or the eye ray with respect to this point when I have to render that pixel.
yes.
Okay. But here I am accounting for what it would have reflected to this object.
So at a time we show the path of one ray.
At a time you show the path for one pixel.
The ray from one ray.
Right. So then you are also looking at what is happening with respect to the light sources. So to decide whether that point gets into a shadow or not, and so on. Right. Okay. So when you show, so there is a window which is a 3D window, which we call it as, let's say, simulation window, where this interactive process is going on, right, where one can probe for any pixel ij or xy what is happening, right. That is your simulation window. You also have a ray traced image, the final image which you would obtain, right, in another window. Right. So this is your simulation window where you can see this whole process, and there is also a 2D window which just gives you the image, the ray traced image. Right. So in fact you can do an interactive building up of this image also, right. So you scan with respect to all these pixels what is happening and just put that point here, render that point here, right. So you have understood what is required.
So this tracing the path of one ray is fine. Now could you just explain how do we get the complete image?
This image, see, this complete image is what you would obtain as a final intensity for that pixel
on the view plane.
on the view plane.
So both are view plane. I mean,
No, this is not a view plane. This is the complete pipeline. And see, this is I. There's a viewing plane there. There's a scene there, right? And the ray starts from I, goes to the viewing plane, sees what happens with respect to the scene, right? I'm able to trace the ray where all it goes, what all objects it intercepts.
but tracing
that-
only the ray from a pixel on the view plane.
That's right.
So the
It definitely corresponds to a point on the ray traced image. That's what I'm going to finally render.
so
So basically, simulation window also includes the ray traced image. That's
Well, that
There's a
you may
subject-
want to include, you may not want to include, because in order to be able to show, clearly on the screen, you will have to, when you display the particular pixel on that viewing plane. So, what are you going to display? The point, right? So that may not capture the true coloration of the pixel. So the best thing is that you have this simulation window which just indicates a point on the viewing plane, which of course corresponds to a pixel on the ray traced image what you have rendered.
What we read as the terms, the local illumination, the reflected, so those were illumination terms.
Right.
How do we get the color
Oh,
at this point?
that we have actually already discussed, right? This illumination term is nothing but it's a tuple.
So,
If I am talking about
combination
a color RGB, then it's a intensity defined as a vector RGB, right?
So in this split window, on the left we have a single ray for simulation window.
Right.
So on the right, the ray traced image, you mean we'll show that particular pixel on the window.
No, here I am actually asking you to give me the entire picture.
So on the
Okay.
left you have just a single
But
ray.
I am also suggesting, this is sort of a suggestion which you can add on, that I can do a sort of a scanning of the entire viewing plane and simultaneously displaying what is happening as the result on that scan to this image. So it's a complete interactive process of generating a ray traced image. Right?
So we can scan through all the pixels and then
Exactly. Right. So is it clear? Any doubts? Is what is needed for the assignment? Okay, when I said that the scene should comprise of the objects of the kind sphere and plane, it does not mean one sphere and one plane. Right? It means that the scene is consisting of several spheres and several planes. So the planes could actually help you to envelop the scene having the spheres, so that you have walls and ceiling and things like that. Fine. So you should be able to produce results like this, which we have seen examples of. Right. So refraction, reflection, specular, right? And you can also set other parameters as input parameters, like depth of recursion, right? So this is the one level ray tracing where I don't need any reflection, then here I have reflection and so on. So this could also be given as an input parameter. Fine. Though I am not asking, but those who are interested can incorporate the transformed objects. So I am talking about sphere and planes, but then you can, for instance, generate scene with objects which are transformed from sphere and so on. Right? Then you need to do the transformation of the ray. Okay. But the more emphasis on this assignment is towards the building up of this simulation. Okay, so you can see the process. You can even try to see it as an animation, that the ray starts from eye, goes to the viewing plane, goes to the other object, goes to the other object, and so on. So you can even do some fancy animation. Fine. And the objects which you display it in the simulation window, that would be through OpenGL, right? On the simulation window. So simulation window is nothing but OpenGL window basically. Everything is happening using OpenGL. Fine. Okay, so that was your assignment 3. right? So due date is 25th, as we already have announced it. I have not posted it on the course web page yet. I'll do that. Okay.
Also the slides.
Yeah, also the slides. Okay. So now there are certain other small issues which are related to ray tracing. I'd like to continue on it. So the first thing is that we have talked about constructive solid geometry, CSG. If you recall, we were talking about this solid modeling, right, earlier. So in fact, we can do the ray tracing of these objects also fairly easily. Okay. So what is this constructive solid geometry? It's basically building up of compound objects using Boolean operations. Right. So for instance, there is a surface or object S1, there is another object S2, right, and I am interested in getting an object of this kind, which is, let's say, a lens kind of an object. So all I need to do is perform a Boolean operation of the type S1 intersection S2 to get this. All right. So as a representation, I can see this in the form of a tree, right, where I have the leaves here as the surfaces, the primitives which are being used for forming the compound object, and then the node above is the operation which I am performing into these leaves. Right, so this is the intersection here. And in fact, you can think of also using a transformation, let's say T1 and T2, which could be associated to these objects S1 and S2. Right. So now let's say, given that you are able to do this construction of compound objects using simple primitives, and let's say these are the primitives with which we know how to get the ray intersection done, right? So if you are attempting to do the model of this, which is S1 intersection S2, then how would ray trace can be used? Right? That is what we are trying to look at. So it's fairly simple. So if you look at what we try to observe is the ray insight test. Right? Ray insight test. So when I was talking about two surfaces S1 and S2, if you look at the ray insight test, that means what is the span of t's, parameter t's, for which the ray is inside the object, right? So with respect to this, there is an intersection at T1, there is an intersection at T2. With respect to this, there is an intersection at T3 and there is an intersection at T4. Okay, and these define the ray insight with respect to each of these objects. Right? And if, let's say, one is interested in looking at what happens after you apply a Boolean operation to the ray insight test, then it turns out that it is merely the Boolean operation applied on these spans of t's. Okay. So for instance, if I look at this as a t axis, for S1, this is the span, let's say from T1 to T2, which is displayed here in blue, right? For S2, I have from here to here. Okay. Now, the ray insight test for the object which is obtained as a Boolean operation of intersection is nothing but the intersection of the spans here and here, which is this yellow line now. So, this gives me the ray inside for the compound object, and that is what I should be interested in when I am performing ray tracing, right. One of them would give me which is the nearest point, and therefore I can display it, right. And these are nothing but the regular intersections with the simple primitives, right. So, if I was to find out the ray inside test for the union, then all I need to do is take the union of this and this, which would give me T1 and T4 as a span, right. Similarly, if I am performing an operation of difference S1 minus S2, then the same operation can be applied on to the T spans, right. So, constructive solid geometry can be easily used in the context of ray tracing without doing much, without doing anything. In fact, it is just there, right. So, explicit intersection you are determining only with respect to the simple objects, and then it is just a matter of using an appropriate data structure to be able to decide what is the point of intersection for the compound object. Right. Okay. So, now the other feature which we wanted to discuss is texture mapping. Texture mapping in itself is a subject and not necessarily related just to ray tracing, but we are going to look at in the context of ray tracing, so that if you want to add to your ray tracing, you can. Okay. So, texture mapping is something like when you observe a scene rendered in this fashion, where you have objects here and these are, let us say, the walls. So, if you just supply the material properties of these objects, which are defined in terms of planes and boxes, you can generate such a scene, right. You can render scene like this. However, if you know that this wall is actually made up of bricks, right, and this material is something like which is more like a thermocol, right. So, how do you add those details on it, which what you see it on the right side. So, here you see some patterns. So, here the bricks are shown, here you see some kind of a texture on this material, right, and there is some pattern on this, there is a pattern on this on the floor, right. So, the question which is asked is, how do we generate such effects? Any suggestions? Use texture mapping, right. Okay. So, see, one may argue that since it is a part of the modeling, after all, when you construct a wall, it's made up of bricks, right, which is an element of modeling. So, why not do that as a process of modeling, right, which is to say that if I am interested in getting the surface details like brick, right. So, one option could be that I do a detailed geometric modeling of the wall, wherein I can define all the variations and details of these bricks, right? So clearly that's a very expensive task, right? And will require lots of storage, and it may be unnecessary from the point of view of what you want to generate as a visual effect, right? So another way to do is that you sort of use combination of geometry, which is the definition of walls as, let's say, planes, and texture mapping, which adds details to this geometry. Right. So in a crude form, what is texture mapping? Texture mapping is nothing but it's like a wallpaper wrapping around onto the object, and wallpaper is nothing but is some sort of an image or a pattern which you paste it on the top of the object. Right. So how do we perform this texture mapping? What are the requirements? So what do we have? We have, let's say, an object which could be defined as a parametric object, say x uv, y uv, z uv, where uv are the parametric domain or the parameters on which the object is defined. Fine. And a texture is nothing but another definition on parameter, let's say S and T, which could be an image or which could be some procedurally defined texture, right? So this is a two-dimensional image texture through the parameters S and T. So S and T just could be the pixel definitions of the image or the pattern you want to paste on, right? And the object could be defined in this fashion, where you have an object here through a parameter u and v, just like your parametric surfaces or a sphere or any other object, right? So what is it that we are trying to do through texture mapping? Is to associate a point on this surface, the object, right, with the image in texture, right? Because ultimately I want to put this pattern on the top of this, right? So what I need to do is associate a point here to a point here, right? So in other words, I need to have what we call it as the texture coordinates S and T added to the coordinate of this point or the surface, right? So that's what we basically mean by texture mapping, right? So in other words, we are trying to look at a mapping function which takes you or which helps you defining the association of u with st, and similarly association of v with st through functions, say f and g, right? It's a function mapping of u, v and s and t, and vice versa, where you associate s and t with u, v through functions h and I. Right. So a simple way of looking at it is that if I have a linear mapping, that means u is related to s and t through a linear function, right, where I defined u as a linear function of s, where u is equal to as plus b and v is equal to ct plus v, right. Then I can associate the parameters of the surface UV with the texture. Once I associate this parameter, I can associate the 3D point of the surface. Right?
This is a one-to-one mapping. That is, for every point on the surface, you have a point on the texture description.
That's what we are trying to do. Yes.
So then, sir, if you want to create a wall, then it's not enough to just have the texture of one brick. We need all the bricks.
Yes, yes. So we are coming to that. So basically, this is a matter of defining these mapping functions, right, with the parameters of the surface to the texture. Right. So if you want to see it in a little more illustrative form, what we are saying is that there is a surface patch or some other parametric surface defined through UV, and there is this pattern here for texture TSS, SNT, and I want to take this and put it on here, right, and then which undergoes the projection transformation, because ultimately what I am going to have is what I see the object on the screen, right. So this object, which is a 3D object, gets further transformed into the screen coordinates, right. So this is we refer as a forward mapping, right. So I try to associate the object with the texture and then perform the projection transformation to get what happens to the object when we see it on the screen, right. Now there could be another way to look at the process where I see it in just the inverse order. That is, I have the screen, I have a pixel here, right, and I try to look at the pre-image of this pixel onto the texture, right. So it's an inverse mapping, right. So that's what you have it in ray tracing. You start from a pixel, right, and you, let's say, have the mapping between the object and the texture. Then you can associate the object to the texture and find out where this pixel would map to the texture, right. So the issue is, what do we do with this? We have established the correspondence as to what this pixel or the point on the surface has got with the texture, right, or a point on the texture. So what do we do with it? See, eventually I have to render this pixel, right, and I know that this corresponds to this texture. So in some sense, I have to incorporate into the illumination or the color of the pixel, right. So in the context of ray tracing, where you are using the illumination model using diffuse reflection and other terms, right. So the material of the object is defined through the diffuse coefficient, the KD, right. That is what captures the color of the object. So what you need to do is modulate or replace that KD through this texture information, right, because what we are saying is that now the color attributes will be taken from the texture, right. So your KD terms will be modified. Is it clear or not? Because what do we want to do? We want to capture the information, whatever is there in the texture, the image of the texture to render this pixel, right? And the mechanism I have is through the material definition of the object, which is through KD, the reflective coefficient, right? Okay, so you can add texture mapping in your ray tracing. Okay.
So, but the
Yeah.
texture on the left side, it may be a shade of colors. So we'll take the.
Yeah. So there are certain issues here. See, if this was a mapping from one pixel to one point in the texture, there is no problem, right? But the small pixel may actually get mapped to a larger portion in the texture. Then what will happen is, this is a similar effect as we have already studied aliasing, right? So one may try to do is that take this information and take an average of the information which is there in this texture and put it there. Because if you just map to, let's say, the centroid of this or one corner of the texture, then it may give you artifact. Ideally what we are saying is that this whole area is actually getting mapped to this pixel. So I should have a measure of averaging the information onto this entire area and put it here. So that way I can avoid aliasing or reduce aliasing, not avoid. Fine. But if you are willing to implement texture mapping in your ray tracing, don't worry about aliasing. Okay. That means you can even consider one of the points here. Take a centroid of the area. Fine. Okay, so now I am coming to the query raised here. So typically, if you look at the examples where one uses these textures, are patterns of this kind where you have, let's say, bricks or a skin or some other pattern, right, which is pasted on the entire plane or entire object, right? And if you are starting with a small pattern of this kind, right, so clearly it requires a repeat of texture, right? So in some sense you would require some kind of a tiling, right? So the issue which are concerning here, when you do tiling, then there is a possibility of getting the seams, right, discontinuities where you do the tiling. So how do you resolve that? Seaming means if I take this, put the same pattern adjoining this pattern and so on, just to build it a larger tile, right, larger texture. That's what I mean by tiling. So clearly at the boundaries I will see a discontinuity, right? It's not going to have a smooth joining. So there are issues related to that, which we are not going to talk here. Okay. So there are ways by which you can almost eliminate, if not fully, this artifact. So given a small texture image, you can actually enlarge it to whatever size and scale you want to, without having this effect of discontinuous boundaries. Okay. Now there is another issue. See, what we have talked about is taking a texture image and put it on the top of the objects, just wrap it around, right? That may not be a desirable thing to do always, right? Let me give you an example here. So here is an example of a little hippo. So this is shown in somewhat wireframe kind of a display. This is a shaded display. This looks quite good. And this is a texture map display. Flipped. So the issue here is that you have let's say you are given an image of the hippo, right, and you have this model also. Remember, this image is a 2D image. You have to wrap it around, right? And when you do this wrap it around, you need to establish a correspondence of the features you want to have association in the model and the texture. Otherwise, the texture of the nose will go to eyes in the model. You don't want that. Right? So that's also an issue. Just not taking the image and wrapping it around the object. You need to do more than that. You need to establish the correspondence of features. Eyes should go to eye, nose should go to nose, and so on. Right? And there are also issues. See, we have talked about parametric definition of surface of the object, where you could define the object in terms of u and v, and you have a mechanism of associating these u and v to S and T of the texture. Right? What happens if you don't have the definition in u and v? Let's say if you have just a polygonal mesh, how do you do the texture mapping for those objects? Right? So there has to be a way of either defining those parametric representations of these objects and then do the association of these parameters to the textures. Right? So this is a subject in itself. Right? So here I have just basically illustrated you how you can use or incorporate in the context of ray tracing. Because all you need to do is, if you go back, is to look for the color or the attribute in the texture image with respect to the pixel you want to render. Right? Fine. So let's stop here. And you must start your assignment soon.